Welcome to the deep dive. Today, we're diving into something fascinating, the Cantor Set, but with a twist.
A geometric twist, you could say.
Exactly. We're looking at it through the lens of hyperbolic space. Think of it as a way to really see this complex idea without getting lost in equations.
And the Cantor set itself, it's one of those ideas that really challenges your intuition.
Totally.
You start with just a line segment, say from 0 to 1, and you just chop out the middle third.
Simple enough.
Seems like it. But then you do it again to the pieces left over, and again, infinitely many times.
And that's where it gets weird.
Because what you're left with, this dust of points, it has mathematically 0 total length.
Zero length.
It contains infinitely many distinct locations on that original line.
How is that possible? It feels like a paradox.
It messes with our basic ideas of size and dimension.
How do we describe the points that remain? Is there a pattern?
And this is where base 3 numbers become incredibly useful.
Base 3, using digits 0, 1, and 2.
Exactly. The points that survive this infinite chopping process, they're precisely the ones whose base 3 representation only uses the digits 0 and 2.
Wow, okay, so the ones get removed somehow.
Removing the middle third corresponds to removing numbers that would need a 1 at that position in their ternary expansion. So it's like a code.
A code. 0 means go left, 2 means go right, and 1 means you're out.
That's a great way to think about it. It maps this geometric cutting process onto a sequence of choices, left or right.
Which sounds a lot like computer science, binary decisions.
Absolutely. It connects geometry to information, to discrete choices.
Okay, so we have this infinite dust cloud of points, 0 length, coded by infinite strings of 0s and 2s. The big question then is, how do we visualize this?
How do you draw something that's infinitely complex but takes up no space? It seems impossible in our normal flat view of the world.
Our Euclidean space.
And the surprising but really effective answer is we need hyperbolic space.
What's wrong with good old flat space for this?
Think about something that grows rapidly, like a family tree going back generations.
Okay.
If you try to draw that on a flat piece of paper, what happens?
It gets messy fast, everything overlaps, branches run into each other, you run out of space.
Flat Euclidean space doesn't expand fast enough to accommodate that kind of exponential branching without everything getting squished together.
I remember seeing an analogy about trying to flatten an orange peel.
Oh, that's a perfect one. You can't do it without stretching or tearing it. Right? There's intrinsic curvature.
So trying to force these hierarchical things like the Cantor Set structure onto a flat plane is like flattening that orange peel. It just doesn't fit naturally.
The infinite branching nature of the Cantor set, implied by those infinite ternary strings, needs more room than flat space can offer without distortion or collapse.
Okay, so if flat space is out, what exactly is this hyperbolic space? You mentioned non-Euclidean.
So Euclidean geometry is flat. Think of a tabletop. Hyperbolic geometry has constant negative curvature.
Negative curvature. What does that look like?
The classic analogy is a saddle shape. You know how it curves down along the horse's back but up along the sides? Imagine that saddle shape, that specific kind of curvature, extending infinitely in all directions. That's the intuitive idea.
Infinite saddle.
Yeah.
What does that curvature do to space?
The absolute key property for us is how space grows around a point. In flat space, the area of a circle grows with the square of the radius.
Pi r squared.
But in hyperbolic space, the area or volume in higher dimensions grows exponentially with the radius or distance.
Exponentially.
Yeah, much faster. As you move away from a point, the amount of space opening up around you just explodes compared to flat space.
That sounds like exactly what we need for the Cantor.
Bingo. As the Cantor set construction branches infinitely, creating more potential points defined by longer ternary strings.
Hyperbolic space provides this exponentially growing room so all those branches can exist without crowding each other.
It's the perfect container for structures with infinite branching detail.
Okay, this makes conceptual sense, but how do we actually draw it or work with it? You can't carry an infinite saddle around.
We use models, and a really common one is the Poincaré disk model.
What's that?
Imagine a standard flat 2D circle, like a disk on your table. We use the inside of that disk to represent the entire infinite hyperbolic plane.
The whole infinite plane inside a finite disk. How?
The trick is the metric, how we measure distance, the boundary, the edge of the circle. In this model, it's infinitely far away in hyperbolic terms.
Infinitely far.
Right.
Okay, mine's slightly blown.
It takes getting used to. As you move from the center of the disk towards the edge, the hyperbolic distance starts to stretch out. A tiny step near the edge in our normal view could be miles long in the hyperbolic reality of the disk.
Distances blow up near the boundary.
Exactly. That's how the finite disk can contain an infinite amount of hyperbolic area. Things look squished near the edge to our Euclidean eyes, but hyperbolically, they're incredibly far apart.
So our usual rulers don't work there.
You need the hyperbolic ruler.
What about straight lines? What's the shortest path between 2 points in this weird disk?
We call them geodesics. In the Poincaré disk, there are 2 kinds of paths. Either they are diameters straight through the center of the disk.
That makes sense.
Or they are arcs of circles that hit the boundary of the disk at a perfect 90-degree angle.
Circular arcs is straight lines.
Okay.
Definitely not Euclidean geometry anymore.
It really forces you to rethink basic geometric concepts.
So we have this model of hyperbolic space, where distance stretches infinitely at the edge, and straight lines can be curved arcs. How do we put the Cantor set in there?
This is the really cool part. Remember, the Cantor set construction is like a sequence of choices. Left third, 0, or right.
The binary decision tree.
We can embed that tree directly into the Poincaré disk, put the root, the starting interval 0, 1, right at the center of the disk.
Okay, so there's a start.
Then the first choice, left 0 or right 2, corresponds to 2 branches moving out from the center. One goes slightly left, one slightly right.
And the next choice.
For each of those branches, you branch left 0 or right 2. These new branches move further out towards the edge of the disk.
Each level of the tree, each additional digit in the ternary string pushes the points further out radially.
You can use those hyperbolic geodesics we talked about, those diameters or arcs, to represent the edges connecting the nodes in this tree.
And because the space expands exponentially out there.
Even though you're adding more and more branches at each level, there's always enough hyperbolic room for them. They don't crash into each other or get visually cluttered like they would if you tried to draw this in a normal flat disk. The hyperbolic expansion keeps them separated.
An infinite path through this tree, an infinite sequence of zeros and twos. Where does that end up?
It ends up at the boundary of the disk, that infinitely distant edge.
The points on the boundary of the disk
are
the Cantor set.
Each point on the boundary corresponds uniquely to one of the infinite number of points in the Cantor set, defined by its infinite ternary string of zeros and twos. The boundary represents the limit of this infinite branching process.
It maps this abstract number set onto the boundary of this geometric space.
It is an elegant visualization.
Now, you mentioned the Cantor set has that weird fractional dimension, right? Log 2 over log 3, about 0.63.
Yeah, the Hausdorff dimension.
How does that fit into this picture? Does space explain the dimension?
It's more of a conceptual connection, I think. The fractional dimension reflects the set's self-similarity and how it partially fills space as you zoom in. The exponential nature of hyperbolic space provides a geometry that naturally accommodates this kind of scaling. The number of branches in our tree grows exponentially as we move out hyperbolically. It's like the type of growth in the space matches the type of structure in the fractal.
So the space's exponential expansion resonates with the fractal scaling property.
It provides the right kind of room for that fractional dimension to manifest without collapsing or filling a whole dimension. There's an intuitive fit there.
Gotcha. And you mentioned this isn't just theoretical. People actually code this up.
Oh, absolutely. You can use tools like Python with math libraries or specialized hyperbolic geometry software.
How does that work?
You'd start by placing the root node at the center of your virtual disk. Then, recursively, for each node, you calculate the positions of its children nodes,
making them further out.
You increase their hyperbolic radius based on the recursion depth and give them some angular separation. The key is using the formulas for the Poincaré disk metric to calculate the hyperbolic positions correctly.
So the code needs to understand that warped geometry near the edge.
Exactly. You might make the hyperbolic step size constant or even grow it exponentially. And while the visual angle between branches might shrink as you get near the edge in the Euclidean view,
in hyperbolic terms, they stay clearly separated because the space is stretching out.
The visualization lets you see deep into the branching structure within the finite circle boundary.
Okay, pulling this all together, what are the big takeaways? Why see the Cantor set in hyperbolic space?
First, it gives you a much clearer, more intuitive picture of how the set is constructed. You see the decision tree unfold.
Makes that infinite process feel more concrete.
Second, it's a fantastic demonstration of why non-Euclidean geometry is useful. It shows that some structures, especially those with exponential growth or fractal detail, are just better represented in curved space. Hyperbolic space is the natural home for them.
The problem, better than flat space.
Definitely. And third, it reveals these really nice connections between seemingly different areas, discrete processes like the Cantor construction, fractal geometry, decision trees from computer science, and this abstract non-Euclidean geometry.
It ties things together.
Yeah, it shows how different mathematical languages can describe the same deep structure.
So for everyone listening, the main point is hyperbolic space isn't just some weird mathematical oddity. It's actually a powerful tool for visualizing things that seem impossibly complex in our normal view.
Absolutely. Things like the Cantor set with its infinite branching.
It makes the limitations of our standard flat space really obvious when you try to cram that kind of infinity into it.
And hopefully seeing it visualized this way as this beautiful branching tree reaching out to infinity within the Poincaré disk gives you one of those aha moments.
It takes the Cantor set from being just a strange definition to something you can almost kind of picture. The infinite nature feels less paradoxical.
It feels accommodated by the space.
What else out there, maybe in biology or network structures, or even just abstract ideas, has this kind of infinite branching or hierarchical complexity?
Where else might our flat space intuition be holding us back?
Could thinking in terms of hyperbolic or other non-Euclidean geometries give us completely new insights into how those complex systems work? Maybe the most natural way to model them isn't flat at all.
That's a fantastic question to ponder.
Thanks for taking this deep dive with us today. Sometimes you find something really fascinating online, or maybe in a paper. But the deeper you dig, the more tangled it gets.
Absolutely. Information overload is real.
Exactly. And you just want the key stuff, the cool ideas, the connections, without needing a decoder ring.
That's what we try to do here on the deep dive. We take that dense material and pull out the really illuminating bits, curate it for you.
Today, we're diving right into a really cool intersection. It's where prime numbers meet fractal geometry.
But you flagged some great sources, and our mission today is to unpack this thing called the dynamic prime Cantor.
The dynamic prime Cantor set. Okay, that definitely sounds like something from a math lab whiteboard.
Yeah, maybe. But the core idea is surprisingly neat. It is a fractal, like the classic Cantor set everyone learns about.
Right, the one where you keep taking out the middle third.
Exactly. That one's got a fixed rule, always the middle third. But this one, this dynamic prime Cantor set, it's dynamic. It changes based on the prime numbers themselves.
Ah, so the primes dictate how it's built.
That's the twist. The standard set is static, predictable. This one has this built-in rhythm, you could say, driven by how primes are distributed. And exploring how reveals some really surprising links between number theory and geometry.
Okay, I'm hooked. Let's get into the construction. How do you actually build one of these things? Where do we start?
Okay, so picture the number line. We start basic. The unit interval, the segment from 0 to 1, let's call that S0.
Got it.
Now bring in the stars of the show, the prime numbers, 2, 3, 5, 7, 11, and so on.
Okay.
And we also need a helper function called the prime counting function. It's written as pi of x.
What does that do?
It's simple. It just tells you the count of prime numbers that are less than or equal to whatever number x you plug in. So pi 5 would be 3 because 2, 3, and 5 are the primes less than or equal to 5.
Ah, so it tracks how many primes we've encountered up to a point.
Exactly. Think of it like a prime density tracker. Okay, so we have our interval, our primes, P1, P2, P3, and our counter. Now for the steps.
How does step K work?
For the kth step, we look at the kth prime number. Now take every little interval that's left over from the previous step. For each of those intervals, you divide it up into pk plus 1 equal pieces.
Okay, so the number of pieces changes based on the prime. 1, 2 means 3 pieces. P2.
And then we decide which pieces to remove. We look at the index j of each subinterval, first, second, third, up to pk plus 1. If that index j is itself a prime number, and it's less than or equal to the prime we're using for this step, then, poof, that subinterval gets removed.
So at step KD, using prime k, you divide into pk plus 1 pieces, and you remove the pieces whose position number index is a prime less than or equal to.
Got it. The number of divisions and the rule for removal changes based on which primes are less than or equal to the current prime.
That is dynamic. It's not just middle third every time. It's recalculating based on the prime sequence.
Exactly. You do this division and removal for all the intervals you had from 1. What's left over makes up the new set.
And you keep doing this
Forever.
forever.
Yes. The dynamic prime Cantor set is what's left when you intersect all those sets. It's the points that survive every single step of this prime-based removal.
Okay, my head's spinning slightly. Can we walk through the first 2 steps, make it concrete?
What's the idea? Start with S0 equals S0 and a linear.
Yeah, so we divide into 2 plus 1 or 3 pieces.
Right. 13, 23, and 23. Now, which primes are less than or equal to?
Just 2.
So we remove the subinterval whose index j is 2. That's the middle one.
So you remove 13, 23.
Exactly. Leaving S1 equals 0, 13, cut 23, 1. So far, it actually looks like the standard Cantor set's first step.
Okay. But the next step will be different. What about the second prime?
Right. Now things diverge. We take each interval in S, that's 0, 13, and 23, 1, and we apply the P2 rule.
Okay, so we divide each of those 2 intervals into subintervals.
4 pieces for each. Now, which primes are less than or equal to?
2 and 3.
Exactly. This means from each set of 4 subintervals, we remove the second and third ones.
Okay, let's trace 0, 13. Divided into 4, that's 0, 1, 12, 1, 12, 2, 12, 2, 12, 3, 12, 4, 12. Remove the second, 1, 12, 2, 12, and third. So we're left with the first and the fourth. Now 112 and 312, 412.
Which simplifies to 112 perfect.
And we do the same thing to the other piece from S1. 23, 1 interval.
Yep. Same process. Divide into 4, remove the second and third. You'll get 23, 7, 12, 12, 1, and 12.
Best do is now 4 smaller intervals, 0, 12, 14, 13, 23, 7, 11, 12.
Exactly. And you can see it's already much more fragmented and less symmetric than the regular Cantor set. The structure is really being dictated by those primes, 2 and 3 in this case.
You can see how the changing rules really start to bite. What kind of object are we left with? What are its properties?
Despite the weird dynamic construction, it actually shares some basic topological traits with the standard Cantor set. It's compact, for one.
Because it's an intersection of closed sets, right?
Yep.
And it's bounded.
Exactly. Intersection of nested compact sets. And it's definitely non-empty. We always keep at least the first and last subinterval at each stage, so points remain.
Okay. Compact, non-empty.
It's also what's called a perfect set, which means it's closed and has no isolated points. Every point in the set is infinitesimally close to other points in the set. It's dense in itself.
Right. And like the standard one, that must be totally disconnected. All those removals must break it up completely.
Totally disconnected is right. Because we keep removing pieces at every scale, infinitely, no actual continuous interval, no matter how small, can survive. You just end up with a kind of dust of points.
A dust of points. And I bet if you try to measure its total length, it's 0.
Yes, just like the standard Cantor set. The total length of the pieces we remove adds up to the full length of the original interval.
It can't be empty. And if it's a perfect set, it must have tons of points, uncountably.
Yes, any non-empty perfect subset of the real line is uncountable. So it has as many points as the real numbers themselves, even though its length is 0.
Okay, 0 length, uncountable points, totally disconnected.
Yes.
You mentioned something getting really interesting with its fractal nature, the dimension.
Ah, yes. The Hausdorff dimension. This is where things get really wild and where the prime connection shines.
So what is it for this dynamic prime set?
There's a formula to estimate it after steps. It involves the number of pieces kept at each step, which is pi plus 1. It looks like ln pi plus 1.
Whoa, okay. Logs and sums involving primes and pape looks intense.
It does. But the crucial thing is what happens when k goes to infinity. We need the limit of that expression. And that's where, amazingly, the prime number theorem steps in.
The prime number theorem. That's the one that approximates, right?
Yeah.
Tells us primes get sparser. How does that relate to a fractal dimension?
The theorem says is roughly ln x for big X. If you substitute that approximation for the dimension formula and do some non-trivial calculus and limit analysis, the actual Hausdorff dimension of the dynamic prime Cantor set turns out to be 1.
1. Seriously.
Seriously. It has 0 length. It's disconnected. How can its fractal dimension be 1, like a line segment? It means that despite being just dust, it's incredibly thick or dense in a fractal sense. It occupies space almost a line does, dimension-wise.
Wow. So the way the primes force the removals isn't aggressive enough to push the dimension below 1.
Exactly. The proportion removed at step y, which is pi plus 1, behaves kind of like 1 ln pi thanks to the prime number theorem. That fraction goes to 0. Yeah, but it goes to 0 slowly enough that the cumulative effect doesn't reduce the dimension.
So the prime number theorem isn't just some abstract analysis result. It's literally embedded in the geometry and the dimension of this set.
It really is. The dynamic nature, the prime-driven rules, it highlights how different it is from static fractals.
Let's talk more about that dynamic part. You said the primes introduce a kind of rhythm.
Think about it. Unlike a fractal where the rule is the same forever, each new prime forces a whole new round of refinement. The scale changes, 1 pk plus 1. The removal rule changes pieces out. It's constantly adapting to the next prime.
So the irregularity of the primes gets baked right into the fractal structure.
Deeply baked in. And think about prime gaps. The gaps between consecutive primes.
We know those gaps can be irregular, sometimes small, sometimes huge.
Exactly. So if you have a prime followed by a relatively large gap before pk, dividing into pk plus 1, it applies, then the next prime is far off. It creates a kind of pause or stability.
Like a breathing rhythm, periods of using one rule, then maybe a big jump when a much larger prime comes along after a gap.
That's the idea. Periods of relative stability in the fractal generation, punctuated by potentially more disruptive changes when the next prime arrives, especially if it's significantly different or follows a large gap.
The geometry might reflect things like how often twin primes appear or how big prime gaps get.
That's the really tantalizing speculation. Could the fine details of this set encode information about prime distribution? Could studying its geometry tell us something new about, say, the Riemann hypothesis or Kramer's model for prime gap?
Wow, that's purely speculative, you're saying.
The connection is so direct it makes you wonder. The primes build the geometry. It's not unreasonable to ask if the geometry reflects the prime's deepest properties.
Mind blown. There's another layer too, something about hyperbolic geometry. Why bring that in?
Hyperbolic geometry, specifically the Poincaré disk model, turns out to be a surprisingly natural place to visualize and analyze this DPC set.
That's the weird circle map, where straight lines look like arcs and things shrink towards the edge.
That's the one. The boundary of that disk represents infinity. We can map our original interval onto that boundary circle.
Okay, so our fractal now lives on the edge of this disk.
Exactly. And the construction process, we can visualize it inside the disk. It becomes like growing a tree, a geodesic tree. Geodesics are the straight lines in hyperbolic space. They look like circular arcs hitting the boundary perpendicularly in the disk model.
So a tree is branching out from the center towards the boundary.
Towards the points representing our interval. Think about the removals. Using prime, the subintervals we removed on the line correspond to certain arcs on the boundary disk. Those become forbidden targets. Any branch of our geodesic tree that was heading towards one of those removed boundary arcs gets pruned, cut off. It's not allowed to reach that part of infinity.
So the primes are acting like pruning shears on this hyperbolic tree.
Beautifully put. The prime sequence dictates exactly which branches get pruned at each stage of the tree's growth.
And the dynamic prime Cantor set on the boundary is what's left. The points the tree can still reach.
It's the set of limit points on the boundary that are accessible to the tips of this infinitely growing prime pruned hyperbolic tree.
Why is hyperbolic space good for this?
A couple of reasons. One, it elegantly handles the infinite refinement within a finite picture about the disk. Distances, too. The natural exponential branching of trees fits really well with the metric properties of hyperbolic space.
The fractal on the boundary is like a fractal shadow cast by this prime-driven process happening inside the hyperbolic disk.
That's a fantastic analogy. A fractal shadow. Sparse because of the zero measure, but incredibly intricate and dimension 1 thick because of how the pruning happens.
Okay, prime curvature.
Yeah.
That sounds even more intense.
Yeah, this is pushing the interpretation further, but it's built on the previous ideas. We can try to quantify the disruption caused by prime gaps. Define a prime curvature based on the next gap, but normalize it by the local density of primes, which is related to log p. So something like Krauke k plus 1p.
A bigger gap relative to the size of the primes means higher curvature.
Think of it as measuring the unexpectedness or size of the jump to the next prime. A large gap gives a high curvature value, a shock in the prime sequence.
How does that translate to the geometry? To the hyperbolic tree or the fractal shadow?
The idea is that these high curvature points, these large prime gaps, might correspond to more significant events in the hyperbolic construction. Maybe more drastic pruning, or a sudden change in the branching pattern of the geodesic tree.
Geometric ripples or shock waves propagating through the structure because of a large prime gap.
Geometric shocks, periods of smooth refinement punctuated by these abrupt changes driven by the prime gaps. And these shocks could locally affect the fractal's properties,
making the fractal thinner in regions associated with big gaps.
That's a plausible consequence. If a large gap leads to more severe pruning locally in the hyperbolic tree, the resulting fractal shadow on the boundary might be locally less dense, maybe even have a locally lower dimension in that region. It suggests an anti-correlation. High prime curvature might lead to lower local fractal dimension.
Wow. So the texture of the fractal might vary depending on the local statistics of the prime gaps. That's incredibly deep.
It connects number-theoretic irregularities directly to potential geometric variations.
This whole journey has been amazing. We started with just tweaking the Cantor Set rule using primes.
All right.
And we ended up with zero measure but dimension 1, connections to the prime number theorem, this elegant hyperbolic tree picture, and potential geometric shocks tied to prime gaps.
It covers a lot of ground, doesn't it?
Summing up this deep dive,
Yeah.
what are the key takeaways?
One, the dynamic prime Cantor set is fundamentally different because its construction rule evolves based on the prime sequence. It's intrinsically linked to number theory.
Okay, the dynamic prime-driven construction.
Two, this link isn't superficial. Properties like its Hausdorff dimension being exactly 1 are direct consequences of deep results, like the prime number theorem.
Dimension 1, despite 0, measure the surprising thickness.
The hyperbolic geometry perspective isn't just pretty. It provides a natural framework to understand the infinite refinement and visualize the impact of prime irregularities, like gaps as pruning events or shocks.
The hyperbolic tree.
And overall, just the sheer unexpectedness of this connection. How the abstract sequence of primes can literally sculpt such a specific, intricate geometric object.
It really does feel like a bridge between number theory and geometry.
It challenges us to look for more connections like this. It shows how mathematical structures can resonate across different fields.
This has been fascinating. Seriously fascinating. It just makes you think, what other patterns are lurking out there, waiting to be found at the intersection of different mathematical ideas?
Absolutely. For anyone listening who got intrigued, definitely explore more about fractals or prime number theory or hyperbolic geometry. They're all rich fields on their own.
What if you use a different number sequence to build a fractal? What would that look like?
That's a great thought. The DPC set feels like it could be just one example of a whole class of number theoretic fractals. Definitely feels like there's more to uncover there.